about the Weil conjectures for projective curves. Because I do not have much time, so I think I have to skip some details. But I think you can find the details on the notes I'm going to talk about. So recall yesterday, we want to compute the zeta function of a smooth projective curve C over the finite field, which is denoted by K. We know that we can write this zeta function as a form of power series. Here the coefficient is given by the number of effective divisors, of degree n defined over the field K. And then we can compute this in the language of divisors. It is given by 1 over 2 minus 1 times this sum minus h. H is some number, which I don't have time to recall. And here the sum is taken, actually this is a finite sum. The sum is taken over the set of representatives of divisors of degree n under the linear equivalence. And by the Riemann-Roch theorem, so we want to compute this number. So under this expression, the only number we don't know at this moment is this exponent. But by the Riemann-Roch theorem, if the degree of the divisor, here the degree actually is n because C is a representative in the set of divisors of degree n. If the divisor is large enough, or to be more precise, as long as it is bigger than 2g minus 2, then the Riemann-Roch theorem tells you that actually this dimension is equal to the degree minus g plus 1, or equivalent is n minus g plus 1. So now if we consider we want to compute the zeta function, we know that this is from 0 to infinity of this an. What is an? An is this number. So this is an, and then n. For this infinite sum, if you consider the Riemann-Roch theorem, you can try to break this infinite sum into two parts. First, you take the sum for those n, which is smaller or equal to this number. So you take the sum from 0 to 2g minus 2 of these monomials. So you get you just keep this term. And then for the other terms, if n is large enough, the Riemann-Roch theorem tells you that the exponent can be computed very explicitly. So we have h times because if for all divisors for all divisors of degree n, for n large enough, all these LC are the same. It is independent of the special choice of the divisors. It only depends on the degree. So in total, here you have h terms of the same expression. So you just break the sum into two parts. For n small, you don't know how to compute these exponents, but anyway, you only have finite many such terms, so these give you a polynomial. And for n large enough, then this term is computable. Then we have such a very explicit expression. And here for simplicity, I denote the first sum by AT. And I denote, so here we have a common factor h, so I just take this, h times the difference of these two formal power series, and the difference of this formal power series I denoted by bt. So the zeta function now becomes 1 over q minus 1 times at plus h times bt. So what is at? At here is just a polynomial. Actually, it has coefficients in the ring of integers. And the degree is smaller or equal to 2g minus 2, because here the largest exponent is 2g minus 2. Okay, so this is at. For bt, because we have such a very explicit expression of the formal power series, we can compute bt. This bt actually it is will tell you the answer. It's the difference of two rational functions. You just do the computation, you can check bt is a rational function. And here, because the zeta function is a linear combination of these two polynomials, of these two rational functions. So if you just, under this expression, you just simplify this expression, it tells you that the zeta function is of the form, it is a rational function, but the only denominator should be 1 minus t and 1 minus qt. And then you have a numerator. But here we only know that the numerator I denoted by lt is a polynomial with coefficients in the field of rational numbers. And moreover, if you really compute this polynomial, you can see that the degree of this polynomial is less or equal to 2g. This is just something you can get by direct computation. And moreover, this is another result we'll need to move through the functional equation. If you evaluate this polynomial at 1, then you get the g, which is the genus operator. So this proves the rationality of the zeta function. Except that I still need to prove that the coefficients of this numerator will actually stay in the ring of integers. But this is true because the numerator is the product of this formal power series and the product of these two linear functions. So if you just multiply them, you will see that the product of this formal power series together with these two linear functions, if you expand this, it should give you a formal power series with coefficients in the ring of integers. But then it tells you that the formal power series, the coefficients of this of LT are all in the ring of integers. So you just take the intersection, it tells you that this is actually an element in the. So this is the proof of the rationality. Now we want to prove the functional equation. Use FE for short. What is the functional equation? The functional equation tells you that Zt should be equal to Q to the G minus 1 times T to the 2G minus 2 times the same zeta function. But you change the variables to be 1 over Qt. So this is the functional equation we want to prove. First, by a direct computation, I call this star. You can show that the star holds if you replace the zeta function by the rational function bt. Because here, for the rational function bt, we have such a very explicit expression. Then you just do the computation by hand. You show that actually the rational function bt satisfies this functional equation. Then, if you want to prove the functional equation for the zeta function, it is enough to prove the functional equation for the polynomial at. Okay? But if we want to prove the functional equation for at, we need to use the Riemann-Roch theorem again. Here I just consider a map. If I have a divisor C on the projective curve C, I just map this divisor to the difference of the canonical divisor. I use this canonical divisor to subtract this divisor, then I get another divisor, which is denoted by C prime. Because the degree of this canonical divisor is 2G minus 2, so this map is a bijection on the sense of all the divisors whose degree is between 0 and 2G minus 2. Okay? This is just because the degree of the canonical divisor is 2G minus 2. On the other hand, by the Riemann-Roch theorem, it tells you that if you want to compute the dimension for the divisor C prime, it should be equals to LC minus degree C minus 1 plus G. You just apply the Riemann-Roch theorem for the divisor C, then you have this expression. That's the relation between these two dimensions. Okay, now I can compute this term. I want to show the polynomial at satisfies this functional equation, so I just compute the right-hand side. I want to compute this. Then I erase the definition of the polynomial at, but if you just use the definition, you'll see that I have the sum. Take the sum from 0 to 2G minus 2, and then you take a C to be in a set of representatives of divisors of degree n on the curve C. Then here you have exponent, a power of Q, and also we have a power of T. Okay, so this is, you just use the expression of the polynomial at, and then you plug in. You'll see that the sum becomes this. But here, this exponent is LC plus G minus 1 minus n. N is the degree of C, so it's this expression, because the degree of C is n. our definition of sigma n. And here, this 2g minus 2 minus n is the degree of C prime. So the sum becomes n from 0 to 2g minus 2, then C in sigma n, this q, the exponent of q becomes LC prime, and then t, the exponent of t becomes the degree of C prime. So in other words, here, the polynomial AT is you take the sum over all the divisors, or you consider all the divisors whose degree is between 0 and 2g minus 2. But here you take the sum for all the C primes. But if C ranges in the sense of divisors, which is between 0 and 2g minus 2, C prime also ranges in the same sense. So by the definition, this should be it's just another expression of the polynomial AT. So this tells you that the polynomial AT also satisfies the functional equation, but the zeta function is a linear combination of this polynomial and this rational function. So combine these two results together to show the functional equation for the zeta function. Okay? And as I remarked last time, the functional equation indicates that, so first, you can check directly by hand. The functional equation indicates that the degree of this polynomial L is exactly 2g. It cannot be smaller than 2g. It must be exactly 2g. And also, the functional equation implies that if you write the numerator LT in terms of the product of linear functions, then the map, which maps alpha to Q over alpha, is a permutation of these 2G numbers. This is, you can check directly by the computation. If you have the functional equation, then this map will preserve this set. So we still need to prove the Riemann hypothesis. In order to prove the Riemann hypothesis, it is enough to prove the absolute value. So recall, what does the Riemann hypothesis mean? It means that these 2G numbers, as complex numbers, they all have absolute value square root Q. But if we have this fact, to prove the Riemann hypothesis, it is enough to prove the absolute value of all these 2G numbers are smaller or equal to square root Q. Because if this is true, that will tell you that Q over alpha I is less or equal to square root Q for all I. Then it means that the absolute value of these alpha i's are all larger or equal to square root Q. Okay? So it is enough to prove this inequality for all I. So I think I still have 21 minutes left. And I try to finish the proof of this Riemann hypothesis within this time. I want to make one more remark before I move on. So this L function, this LT, if you still remember the previous lecture, actually if the curve C is the reduction of an elliptic curve defined over Q mod out by P, then actually this L is just LP. You have just seen in the previous lecture. So to prove the Riemann hypothesis, we need the intersection theory. what is the intersection theory? It's just, for example, the intersection theory is to study the intersection of two algebraic varieties in the affine space or in the projective space. But if you think about the most simple example on the affine plane, you just consider the intersection of two straight lines. Then you have two possibilities. The intersection number, you consider two different lines, okay? Then the intersection of these two different lines might be empty, or maybe they intersect at exactly one point. If the intersection is empty if they are parallel, or otherwise the intersection consists of a single point. But that means if you just consider on the affine plane, the intersection theory may not be very good, because even for two straight lines, the answer depends on the relative position of the curves. So if you want to study the intersection theory, it is much better to consider the varieties inside the projective space. So to start with, I want to define the degree of a projective curve. So what is a projected curve? It is projected means that it is a substance. So K here can be an arbitrary field. It is projective means that the C can be regarded as a subset of the projective n space as a zero locus of some homogeneous equations. So I want to define the degree of such a curve. So in this setting, I do not require the curve to be smooth. This definition is true for general curve. So I will give a definition of the degree of the curve C. So I can define the degree of the curve C to be the degree of a polynomial of three variables. If the C is the zero locus of this homogeneous polynomial in P2, in the projective plane. So if you have in the projective plane, if a homogeneous polynomial f define a curve, then I just define the degree of the curve to be the degree of this homogeneous polynomial. In general, if this C is the zero locus of, say, for example, f1, f2 to fn minus 1 in P to the n, in the projective n space, here these f1, f2, fn minus 1, they are homogeneous equations of n plus 1 variables. Then I can just define the degree of the curve C to be the product of these homogeneous polynomials. What does this mean? It means that in general, this degree, if this C is inside the projective n space, then this C should be the intersection number with H inside the projective n space. Here, this H is a hyperplane in Pn, but here I need to assume that it is in general position. So if you have such a curve in the projective n space, you use a hyperplane to cut or to intersect the curve C, then if the C does not belong to the hyperplane, then the intersection is always a finite many points. Here, I need to assume that this H is in a general position. It means that this H does not tangent to the curve C. So that means if they intersect, then the intersection is good enough. They do not tangent at the intersection point. But you do not need to worry too much about this. So in general, I mean, I can take the hyperplane good enough, and then we have a good intersection, and you can regard the degree as a intersection number.
Do you assume those FIs are
no, actually, this is a good question because this is because of the dimension issues. If in Pn you consider zero locus of a single polynomial, then in general the dimension is lower by 1. And then here the key point here is that after you consider zero locus of n-1 equations, the dimension is lower by at most n-1. It can be bigger than the dimension can be bigger than 1. But if this C is the curve C has dimension 1, so not all actually very few curves can be reached as a locus of exactly n-1 can be defined by exactly n-1 equations. In general, you should have more equations. But if it is exactly defined by n-1 equation, they must be all different, or otherwise the dimension is explicit. So, one more thing is, just as the question indicates, not all the curves can be defined this way. In general, in Pn, if you want to define a curve, you might need more than one n-1 equations. So in general, this definition cannot be generalized to all curves. But this is a good definition. You can just define the degree as an intersection number. Okay? And one more remark is that this degree is different from the notion of genus. The genus is interesting. It does not depend on the embedding of the curve into the projective space. Because for a given curve, you have many ways to embed into the projective space. But the genus is always the same, no matter how you embed into the projective space. But the degree depends on the embedding. If you have two different embeddings, the degree may change.
Do we assume that the polynomials are square free? Or?
Actually, no, because if you just define a curve to be smooth, just to be irreducible and reduced. I mean, of course, if you square it, you get the same zero locus. But I mean, here, if I just consider algebra variety, I always assume it's reduced. But I do not want to consider that because I don't want to talk too much about the algebraic geometry. So here I want to mention the Bizot theorem. If we have two curves inside P2, then I assume that the degree of the two curves are given by D1 and D2. Then if you count the number of the number of the intersection points of these two curves, then it will give you the number can be computed as the product of the two degrees. Here, of course, I need to assume that the two curves are different. Again, here you need to be a little bit careful when you count the number of intersection points because the two curves might be tangent at some intersection points, but we do not consider that special case, or you just assume that in that special case we have a good way to define the multiplicity of that intersection point. Okay, if you define the multiplicity of the intersection points carefully, then this theorem is always true. So I want to generalize this intersection number to arbitrary surfaces. So here I just start from arbitrary algebraic surface.
Next, I remember you said that the degree of curve is dependent on the embedding way of the curve.
Yeah, here I just
the
embed.
number is independent of that, right? But the intersection number of two curves is independent of the way you embed them.
No, it does depend on
But
the.
the degree of the two curves dependent on the way you embed.
Yeah, and these number also depend on the.
But when the degree change, why do we know the product of the still?
Oh, I mean, here in P2, in the projective plane, it is okay. I mean, the intersection is always the product of the degree. But as you see later, the intersection number is a very tricky one.
So do you mean that no matter how we embed the curve into the P2, they always have the same degree? Because the product unchanged.
Yes, actually, if you have a curve embedded into P2, this is a very strong condition on the curve. It must be the zeros of a homogeneous equation of degree d, so the genus must be d minus 1 times d minus 2 over 2. So that's a very strong condition. So I want to generalize that intersection number to arbitrary surfaces. I want to consider on such a surface, if you have two curves, how can I define the intersection number of the two curves? So first I want to define the divisor group on the surface. Here it is no longer the formal finite sum of points. Here it should be the formal finite sum of curves. See here projectile curves inside the surface S, and here the coefficients, they are in the integer, in the ring of integers. So you just consider such formal finite sum, you get the notion of group of divisors over a surface. Here I do not require the projected curve to be smooth. It can be singular.